In this class, we'll be using significant figures to represent the uncertainty that occurs whenever we make a measurement. If we're in the lab and we're measuring a length or a volume or even a mass, there will be some measure of precision in that measurement. So when you report the precision of the measurement, it will be reporting the definite digits plus one estimated digit. So if we're measuring the length of an object, this blue object here, using a ruler marked in centimeters, we would say that this is definitely between 4 and 5, so that we could report this definite digit as 4 plus the estimated digit, and then we'd estimate the percent that the end of this is between 4 and 5, which in this case might be, I would estimate it to be 0.7 centimeters. Someone might estimate it to be 6 or maybe even 8. So you can see that typically we'll have plus or minus 1 or 2 in the estimated digits. So we would report this as 4.7 centimeters, which would have 2 significant figures. Significant figures are meant to represent the uncertainty in measurements, so there are several situations that the rules for significant figures do not apply. For instance, integers. If you can count exactly the number of objects, for instance, if we have a dozen, or if there are 6 people in an elevator, we don't have to worry about the uncertainty of an estimated fraction of a person. Numbers like 1/3, which can be represented to as many decimal places as necessary, or the square root of 2, can also be calculated to essentially an infinite number of decimal places, as can the transcendental numbers like e or pi. Exact definitions. For instance, 1 inch is exactly 2.54 centimeters. The 1 inch does not indicate that there's only one significant figure here. We could, for instance, easily calculate the number of centimeters in 1.05 inches by taking ratios. So in this case, we can use these as a definition and calculate them to as many significant figures as necessary. So if we're given a number, the rules to determine the number of significant figures are, if the number involves the digits 1 through 9, these are always significant figures. So the number 2.34 will have 3 significant figures. 1987 would have 4 significant figures. If the number happens to have a 0 and the 0 is between non-zero digits, such as the number 104, in this case the 0 simply represents that there are no value to the tens units, then in this case zeros between 1 to 9 are always significant figures. So the number 104 will have 3 significant figures. This would also have 4 significant figures. So if there's any number of zeros between, these are always then significant figures. The question arises, how can we determine the number of significant figures in a number like 1040, in which this 0 would definitely be a significant figure since it follows rule number 2. The question arises as to what do we do with the trailing 0. When dealing with a number that has either leading or trailing zeros, we should be aware of the following rules. In general, leading zeros are never significant figures. In this case, the leading zeros will be the first 3 zeros. Often a 0 is put here to indicate the 0 in the units place, so this will have 3 significant figures. These leading zeros are merely placeholders to indicate the magnitude of the number. Trailing zeros, the indication of whether or not they're a significant figure will depend, and it depends upon the decimal place. If there's a decimal point, then we typically count all trailing zeros, not leading zeros ever. So in this case, the number 1020 without a decimal point will have 3 significant figures. If we add the decimal point, that would indicate that the estimated digit will be in the units place, so this will have 4 significant figures. In this case, of course, the zeros are between non-zero digits, so this has 5 significant figures. Many times, however, it's difficult to exactly estimate the number of significant figures from these rules. So for instance, if we wanted to represent the number 3,500,000 to 4 significant figures, indicating that our measurement uncertainty is in the thousandths digit, then we'd have to resort to scientific notation. In scientific notation, we have the form a times 10 raised to a power b. A is the coefficient or the digits, and typically a will be written such that it's between 1 and 10. In the case of scientific notation, all the digits represented in the coefficient are significant. So to represent this, for instance, to 4 significant figures, we could write this as 3.500 times 10 to the 6th, and this would indicate that all of these digits here are significant, so this would have 4 significant figures.